Thank you for taking the time to listen to me here. I'm going to talk a little bit about data science organizations and sort of the challenges many folks face, or at least I faced in multiple places. I don't necessarily know all the answers to how to solve many of the questions I'm going to talk about, but I can tell you a little bit about what we have tried at different organizations I've been at. So let me just go to the next slide. Just to introduce myself, why you should listen to me. I've been in the data science world for the last 9 years or so. I used to run machine learning platforms at a company called Cloudera, along with like some of their big data systems. And then I spent about 3 years and change at Uber, where I ran about 100% data science organization and built a lot of the data systems that are used at Uber, including things like Michelangelo, which is our machine learning platform. So I've worked on both sides of the equation, building the data systems themselves, but also running data science organizations on top, solving specific customer business problems for our business. I currently run product and data science at a startup much smaller than Uber. I think at Uber, we were running with a 400-person data science organization. My current company has like 15, so quite a different scale. But interestingly enough, no matter what environment I'm in, many of the same problems appear over and over again. And it's interesting when you think about data science's evolution. First of all, this is like some made-up title that we came up with 10 years ago and didn't really exist, but the job has existed for decades. You could call them data miners, you could call them data analysts, but a lot of the same kind of tasks used to be performed back in the day. We just figured out a way to get paid better, I think, at the end of the day. So now, having said that, one thing which is interesting about data science is if you look at engineering, when I joined, I used to be a software engineer a long time ago, 2.5 decades ago. And when you joined at that time, let's say you wanted to create a linked list. What you did was you read your computer science book and you figured out how a linked list works, and then you wrote a linked list. Luckily, the world has evolved since then, and there's a lot of composable blocks that you use to build software. You want to build a web server, you hit the web server button on your app and you're done. And unfortunately, data science in many ways still looks a lot like computer science engineering back 20 years ago. And I think we're at the starting point of improvements in how you run data science as a function, moving it more from it's funny because we call it data science, but it feels more like an art form today than it is a science or an engineering activity, whereas computer engineering has generally become more like engineering, like it's more Lego block assembly and less arbitrary creativity, which is still the dominant form of work in data science. I'm going to talk a little bit about these 5 topics. Team composition, how do you scale a data science team? Career growth and expectations. This is interesting because, again, with a new field and an ever-changing landscape of technology advancements like machine learning and things of this nature, people come in with very specific expectations of what the job entails, and the job generally needs more than that. Processes for a high-functioning data science organization. Again, I talked a little bit about this, making it more engineering-like. I want to talk a little bit about how this can apply to a data science organization. You can't apply it generically, but there's things you can do to make it more streamlined. And then how do you make sure you're working on the right things? If you have a large corpus of data, you can spend all your time doing interesting analyses that lead to nothing from a business value perspective. So how do you focus your time and energy on the right things? And then managing life cycles for data science projects. Software projects never end. They continuously require maintenance and upkeep. Good data science projects actually have the same set of requirements. It's just not often thought of that way. So I want to talk a little bit about each of these things. I want to start with team composition. I have a friend, Josh, who's giving a talk later on today, I think at the end of the day today, and he used to say, a data scientist is a person who is just good enough at statistics that they look better than a computer scientist at statistics, but just good enough at computer science that they look better than a statistician at statistics. But the original hypothesis of data science when it started like 14, 15 years ago was that there's this one person who could do all the things you need to get interesting insights out of data. This is building your pipelines, exploring the data, then building models, and then taking it to life using production systems. That world is long gone. There used to be, back in the day, there used to be people who would literally do all of these things as one person, but now it's gone back to a more traditional world where there's data engineers, analysts, data scientists, product managers, ML engineers. Each of these tasks don't even have clear definition, but all of these roles now exist. So when you build a team, I don't think the original vision made any sense, to be honest. Trying to find people who want to do all of these activities, both have the skill and a desire to do all of these activities, was, I think, profoundly misguided. It's just not practical, especially at scale, to have individuals who want to cover every aspect of this. A good data scientist has to have an ability to do any aspect of this, but building an organization purely based on finding people who are going to do end-to-end every aspect of this job, I don't think builds for it sets up for a high-scale organization. So the reality that we live in more and more these days is this decomposition of tasks to specific profiles, data engineering, so on and so forth. And people talk a lot about, hey, it's hard to hire data scientists. In my experience, it is hard to hire good data scientists, but you know what's harder? Data engineers. It's one of these very critical jobs which makes a data scientist successful, but in practice, very few people actually seem to have desire to do it. There's actually a lot of skill required in good data engineering, but it's not necessarily appreciated. I found that my biggest challenge in the Valley for the last 15, 10 years has been hiring good data engineers. And on this note, I want to talk a little bit about the ratios that I've run with in terms of data engineers to data scientists and data analysts. I usually like to run at a 1:1, almost data engineer to data science ratio. I find it very hard to achieve these kinds of ratios because it's just not possible to hire the number of data engineers I need, but that's what I'm constantly striving for. In practice, I'm looking at something like a half a data engineer per data scientist if I'm lucky. So this is one of the big investments that we have found pays off in spades. Having a sufficient volume of data engineers who can actually get data in a usable form, who can maintain the data, deal with data quality issues, model it in a way that makes it easily accessible. When at Uber, I was running with I'm not going to talk about exact numbers, at multi-petabyte scale clusters, and just making sure that you could operate things efficiently would dramatically shave off 1,000 computers, because you don't need that. That's the kind of compute capacity that we would save just by having more efficient representations of data. When you had a good data engineer who could understand the query patterns and optimize for those query patterns. And it is not just, suck data from point A to point B. It is really about how is this data going to be used, creating the right models for, in terms of how you lay out the data. These kinds of things really do matter. Understanding the limitations of your engines that you use to actually run your queries, things of this nature. So one of the big takeaways here, data engineering is probably more important than all the other activities here, and you need that as a foundation if you really want to build a data-driven culture. Types of data scientists. One of the big challenges that's ongoing right now in data science is that the title of data science, people associate it with doing things like machine learning tasks, but everybody wants this title. So now, and the reality is that most data tasks don't require machine learning. Most data tasks require exploration, analysis, and understanding in the context of a business operation. It used to be the case that there was a pretty easy understanding of who a data analyst was versus a data scientist. Every data analyst today sees their future as becoming a data scientist. This is just a given at this point. And in fact, some companies, I think Facebook and Lyft are good examples in the Valley, have basically just changed the titles. They're like, well, we used to call this person a data scientist and that person a data analyst. I'm going to call them all data scientists, but I'm just going to change a few things underneath. And that is, I'll call them data scientist analysis and a data scientist experimentation and a data scientist modeling. And effectively, you create the exact same class system you had before, but you just give out the title data scientist. I'm not sure this is a real solve for the core problem, which is that if you don't give a person a path forward, which gives them a way to grow independent of just becoming a data scientist in the sense that they do heavy modeling activities, they just want to switch because you've effectively created a second-class group of people who are not valued as highly in the organization. But in reality, data analysts often are worth their weight in gold. If I was thinking about some of the scenarios we ran into, and we built some of the machine learning models we built generate things like the ETAs you see in your app in Uber, or the prices that you see and things of this nature. Really foundational elements of how Uber operates. But some of the biggest impact things I've seen actually involve having something like a data analyst who finds that the way we spend marketing budget is not efficient, and it can change allocation of $100 million overnight from one market to another. These activities are unheralded, unappreciated because they're not like a machine learning system. They're literally just an understanding and an analysis of your business, but they can often have significant ramifications to your business in a way just as much as a production machine learning system, which takes a year and a half to build. And so that's one of the big challenges that the industry is facing right now is how do you recognize and create a career path for people who are really good at this deep understanding of data and applying it to business problems. I don't have an answer, to be perfectly honest. I don't know how to do this. We've actually looked at various elements of how to handle this, including both changing the title to data scientist and just giving them a specific focus area, but also looking at things like what is the kind of person we're trying to hire, and how do we give them a title which leads to a right place. So for example, we've talked about strategic analytics or business analytics, things of these nature. Business analytics often, unfortunately, gets confounded with the same problem, but basically having people who are more interested in the business of your, rather than the machine learning or the technical aspects, and are interested in using the data to unlock business insights rather than focusing on the technology side of the house. But when you do this, it's really important to create a distinction between these ladders and give them a successful growth path. Again, I don't know the answer, but this is one of the things that we have been struggling with tremendously, both in my previous companies, but also generally in the industry. And you can see that in the way people have been attacking this problem. The roles have started getting separated out. There is this notion of people who focus on analytics, people who focus on experimentation, and then of course people who are doing machine learning. At the end of the day, you really don't need that many people who do machine learning. You need a lot more people who do exploration of your data. A new and interesting element that's been popping up recently is behavioral data science. And this is really using quantitative methods in conjunction with behavioral economics type theories. So you guys heard from Kahneman this morning. Unfortunately, I was a little jet lagged and overslept that one, but I really wanted to attend. But this is a huge, huge area of opportunity that as businesses, we've still not done a lot to take advantage of. Simple things like how you message, what words you use in an ad can have a pretty profound impact on like conversion ratios. And there's a rich field of study in behavioral economics, which are not just like a psychology-based, like more abstract qualitative property, but also something which can be verified quantitatively. So the notion of bringing in behavioral scientists is a very powerful one. We did this to great effect at Uber. I won't talk too much about the examples here, but there's some well-published examples, including the fact that how do you improve the rate of tipping for a driver? Well, you can do things like you can show somebody a percentage of the fare or a dollar amount. The two make a huge difference in different scenarios. For example, if you show a percentage on a large bill, people are much more willing to do the percentage. If you show you have to pay a $10 tip on a $100 thing, you actually feel like, man, $10 is a lot of money. I don't want to give that tip. So these are the kinds of things that you can actually affect dramatically. It can change the amount of tipping behavior quite significantly if you were to use the right strategies here. And this is something that is significantly underinvested in the industry right now. So one area I definitely would recommend as you look at your data science organizations is how you can potentially leverage behavioral science in your arsenal of techniques for having business impact with data science. And the next one is a little bit more mundane. In terms of grading for growth, people are still working through and figuring out how to evaluate success for data scientists. There's technology and like their ability to understand like complex models. There's their ability to have business impact, like the analytics examples I gave you. But the interesting thing is this has also not been hard specified. Every organization I've seen tends to do things a bit differently in terms of how they evaluate data scientists. We have started going to a simpler approach where it's based on 4 principles. It is scope, which is the size of the domain that you're responsible for. Your impact, which is your ability to make a deep business impact using your capabilities. Your collaboration, which is how well you're able to work with others. In data science especially, I think this is particularly critical. And your technical complexity. Some problems do require deep technical skills, and your ability to use that arsenal to full effect is important. This doesn't mean that you have to be good at all 4 things in order to be successful, because the problem with requiring all 4 of these things is that then people will gravitate towards problems which give you the opportunity to exhibit all of these traits, and there's not that many of them. Again, you don't need technical complexity in every problem, but you can have big business impacts on things which are not super high technical complexity. So how do you manage that is really important. But across these 4 dimensions, we generally feel we can manage things pretty well. The one area that I think generally gets a little bit less emphasis is the collaboration side. I tend to think of data science as sort of halfway in between product management and engineering, in the sense that you're often trying to make a business change, and your understanding of the business context is super important in how you solve the problem. But not only that, your ability to communicate effectively to your business stakeholders and convince them of what you're seeing in the data ends up playing a critical role as well. So there's an element of, I won't say selling, but it actually is selling to some extent, the analysis and insights that you've generated to the organization. And this tends to get underappreciated a lot. Really strong technical person can do all kinds of interesting things, but their effect is significantly limited if they're not able to convince the business that there's a change required in the way that we operate. And again, like a lot of data science problems, there's like some problems which are like, hey, I'm going to build a machine learning model that changes the way the app works. But many machine learning models, let's take a churn model. A churn model by itself is not very interesting, to be honest. The churn model is only interesting in as much as you can do something about the churn, and that really requires a deep collaboration with the business, saying, hey, we can predict with like high accuracy who's going to churn 3 months before they do, but really that's not interesting to you, because you don't want to know who's going to churn. You want to know how do you change this person's churn behavior. So let's talk about what levers you have as a business to do something about it. Maybe you can give them a discount code. Maybe you can remind them of the product's value, whatever it is. And so then you have to change the problem from like detect churn to detect what lever of churn is likely to prevent this person from leaving the business. This is a subtle change, but if you don't understand the business context and you're not able to collaborate effectively with your stakeholders, most churn projects are a waste of time, because that's what happens. They predict very well whether somebody's going to churn, but you can't actually do anything about it. And so you feel pretty good about what you did from a technology perspective. You're like, hey, I solved this really important problem. I can predict with high accuracy who's going to churn, but the business actually didn't do anything with it. This is like a very classic example of data science projects gone bad in general. And so that's kind of what I was getting at with the business stakeholder management and picking the right projects. Churn is like actually a classic example, because it's like everybody wants to do a churn model. Very few churn models result in business improvements. But there are many other such examples where being really deeply aware of what changes you can drive really matters a lot, because many things you can predict don't result in changes to the business. So finding the things you can predict which actually allows you to change the business outcome is really what matters. So then I want to talk a little bit about this notion of like moving towards a more engineering architecture versus art model. We still have a way of working in data science which is, you have a problem, you assign it to a data scientist, they go off and do their own thing, and they work in their notebooks and come up with, do various analyses and come back with you with a PowerPoint presentation that tells you how the world works. This is like so different from how an engineering organization works, and in many ways I think there's a lot to be learned from engineering organizations. I've seen that many data science organizations, even to this day, don't properly use classic development process techniques such as Jira. I think this is becoming more and more common, so maybe this is not as relevant. But even Git and version management, too much work is often saved in people's like laptops, because they don't see this as like a core engineering skill, and they don't see this as important to their life, day-to-day life. But this is like unacceptable at this point. We have to put discipline in our folks to understand that what they're producing, even if it's a one-off analysis, not a machine learning model that's running in production, if that analysis is going to drive a business decision, and I hope most of the projects you're doing are to drive business decisions, it matters. And it matters means you must do it with high quality, which includes things like using Git, because you want to be able to reproduce your results. I mean, most of you are here at this conference presumably because you find the tools that Domino is building are relevant for solving some of these problems. I think this is a big area where the industry has not developed sufficiently, and we really need to as data science leaders, we definitely need to make sure that these kinds of standards are enforced in our organizations. The thing which is different about the development process for data science relative to engineering is the data artifact side of the house. Reproducibility in data science is not just the code. It's actually the data that you use to run the code on to get the results. So how do you do things like data versioning so that you can actually reproduce your results later on? Engineering has this problem, but much more limited ways. Like they have dependencies on other libraries, and when they have a library change, they can break the original code plans. But it's a much more limited version of what we're dealing with, which is every data analysis is done on a specific piece of data. And if you don't maintain that history of what data that analysis was done on, the next time you run the exact same analysis, you'll probably find a different result. Not probably, you're guaranteed to find a different result because data is never that predictable. So that's another thing which is something which we all have to get really good at, which is that when you save, and I talk about Git and version management, that's not the entirety of the story for data science. For data science, this also includes how do you do data versioning? How do you make sure you capture the query for the data that you needed to run this analysis? Libraries and abstractions. Again, software engineering has been doing this for ages. They have concepts of like building libraries and modules and things of that nature. And many data scientists do this too. We can do more of it, but there's lots that people do already. But when we're talking about libraries here, we're talking about things like functions and software packages. But for data science, libraries go beyond pure code snippets. There are libraries of learnings, libraries of features. When you think about your company, I don't know, no matter what you work on, whether you're working on hardware or whether you're working on like a consumer application or an enterprise application, there are certain things that tend to remain constant that matter a lot in data analyses. If you have users, there are a set of things that you know about the user, their lifetime value, maybe, or their how long they've been with you as a customer, their engagement levels, their spend propensities. These are just examples of things that might exist in your business. For hardware, it might be a completely different set of things. For enterprise software, it might be a completely separate different set of things. If you're building like dongles of some sort, it's going to be different. But at the end of the day, while it may be different from business to business, many analyses will require the exact same set of features to start from. And if you don't have a concept of libraryifying these like features, these understandings, every data center will start from ground zero every time. And people do this in a somewhat ad hoc way today where they will share like a pipeline of some sort, ETL pipeline of some sort, but a really well-managed named repository of things like features is extremely valuable because you can actually now use this as a ground zero for the next person to come in and do the analysis. I mean, I would not want people to build independent LTV models of my user base, and nobody does that typically. But what about things like price sensitivity as an element to many models? It's going to be highly relevant as you think about who you're talking to. That price sensitivity model, you probably don't want it to be reproduced. There's 18 different things like this which are elements of your users. Could you put them all in one place? They might in turn be models, but that model output is only done once, and then the next data scientist can actually build on top of the model output of a previous user's model. This is very powerful because it also means that as you improve one of those features, everybody benefits. As you get more granular in your ability to predict things, everybody gets the benefit of that. So this notion of like a librarification of your features and your learnings is extremely powerful in data science. It's not as relevant in software engineering, and something that we really need to proliferate as in data science. Documentation. Again, documentation, this is kind of tied to the libraries thing that I was talking about, but documentation goes well beyond code in data science. We do, notebooks often have markup and you can like document things, but documenting learnings goes beyond just code markup. It's actually about, hey, I understood something about our user behavior. How do I present this to the rest of the organization? And make it accessible. Every time I want to learn about, like, I don't know, not that this is a real example, but in Uber, every time I want to learn about how our drivers behave, is there a place which actually is our encyclopedia of learnings? This kind of thing is, again, super useful, not just for data scientists, but for the entire organization, because you can now start having a ground zero where you can understand the value from a bunch of different analyses that your data science organization has done over time. And then code reviews. Again, this is something that engineering organizations do, some data science organizations do. It doesn't work perfectly, to be honest, in data science organizations for multiple reasons. One of them being that the tooling is really bad for doing code reviews and things like notebooks. But the other is that it's just not a cultural thing in data science. I think this is critical. It's when we make $100 million decision based on some analysis, the fact that somebody could writing code in Python could misspell a variable and have a completely different result show up, and it'll be completely obtuse to you because 120 million looks the same as doesn't look that different from 240 million, but it's a big difference in the actual money being spent. You can't tell which result is right and which result is wrong in a probabilistic model. So it's really, really important to have people recheck the code, but also even that's one aspect of things which is on software side, which is just at least 2 people have read every piece of code before it's used to make decisions. But the other element here is the strategy, the approach you take in data science. Which set of methods are you looking at? Are you looking at the right set of methods to go explore this problem? Are you looking at the right data? Having a project review up front, which is saying, hey, this is the problem I'm trying to solve. These are the approaches I plan to try. This is a good opportunity for other data scientists to both learn what you're doing, which is a good way to expand knowledge across your group, but also have other people give input into the process of discovering insights. Hey, I think you should look at these other features which are really important for this problem. I think you should look at these techniques which are super important for this kind of categorical variable. This kind of thing is super useful pre-running of one of these exercises. And then post-running, having somebody actually say, these are the experiments I did, these are the results I've got. And that way have a chance for people to critique those results as well so that they can actually improve from that process is super important. This is a little bit different from software engineering, which tends to focus on a fairly straightforward design, high-level design, and then the actual code implementation. I think there's a lot more work to be done in how you choose to explore, how do you choose to analyze data. There's a lot more upfront work which can be done where, again, multiple people sharing input can be really useful. We used to do this with not just an email blast. Any project which had of any significance actually had a half an hour, pre-launch, pre-project launch phase where a small data science team would get together and discuss the proposal, and then a post-completion phase where they would review the results. We found this super useful. And then finally, experiments. Now, experiment design is taking, I know how to do basic things like sample size calculation, whatever. I don't need any help. But experiment design has a lot of nuances, and it's really important, again, for experiment design to be done really well. What are the confounding factors that you're controlling for? Does this experiment design, how do you interpret these results? Are you looking at the right metrics? For example, if you choose 2 metrics to focus on and you only worry about those 2 metrics, you might miss 3 other follow-up metrics in the side. It's really important to think through these things, and so we actually included experiment design and interpretation as part of our pre-project start and post-project end reviews as well. And then strong tooling. Coming from software, I think notebooks are the worst thing in the world. They're like garbage. I apologize to all of you who use notebooks on a daily basis, but the notion of having this state change every time you execute things and then being able to go back and edit things is not the right way to do programming at all. It's still very useful, but you can do this better by having specific expectations of having a full run through your application at one point, because that's your actual state. I think RStudio's model is much better than the Python notebook worldview in terms of actually writing high-quality code. There's not much you can do about it, but at least you can start enforcing standards on how people use this stuff. The other thing which is probably controversial is we're all big fans of big data. I came from a company that just sold people big data, and I think it's a must-have in most organizations. But a lot of data science analysis and exploration probably shouldn't be starting with big data. It should be starting with a big-ass computer. It turns out that a single computer actually can hold a lot of data, and multi-core out-of-core processing has become pretty good in things like pandas right now, and it's getting better all the time. You can process 500 gigabytes of data without a problem on a single computer. So giving compute power to your data scientists and having them be able to do things in a more simple environment, honestly, is very powerful, and I think it's underestimated tremendously. Actually, it's not underestimated in the sense that many data scientists do this anyway because it's so convenient, but we all tend to over-preach the gospel of big data. I do think at scale, once you run into production, you do want to work on big data systems, but most analyses should be done off of compute, which is just on single node. I won't spend too much time with the rest of these things, but I think this is kind of obvious. Experimentation frameworks, good experimentation tooling is critical for your success. ETL tools we don't even want to bother about. The one last thing I want to touch upon is path to production. Models have life cycles and they need to be iterated upon. So having a way to quickly take your stuff to production without having engineering in the way is really important. So supporting things like running Python in production, I find extremely valuable because it reduces the number of bottlenecks in getting your updates to production. including things like monitoring of your performance of your models, things of this nature. That's like, I'm going to probably leave it at that because I think I ran out of time for the last slide. But hopefully this is useful as a sort of some of the problems I've actually dealt with in my past while working on large data science organizations. That's all I had. Thank you.